All right, so we left off talking about hypothesis testing and kind of this p-value approach. So just kind of a summary of what we're doing. The first thing we have to do is identify what our null and alternative hypothesis are. We talked about we have two-tailed tests. One-tailed test could be left or right. Kind of changes things in terms of how we find the p-value. So we'll just go through another example here, just kind of continue what we did last class, and then I'll do some work in Excel, so we'll get some more examples from there as well. So once we have that null alternative, we're always going to be given a level of alpha that we want to do this hypothesis test at. So one thing in the last class we talked about, we choose alpha or the type 1 errors we want to make. So alpha represented the probability that I made a type 1 error. Right? So a type 1 error was when I rejected the null even though I shouldn't have been. So when we talk about having alpha values of typically our alphas will be 0.1. This is markers is not great. Let's see if this one works a little better. So yeah, 0.1, 0.05, and 0.01, right? We can think about those as significance levels. So significance levels of 10, 5, and 1%, right? So the probability I make a type 1 error is alpha, so that's 0.1, which means I make type 1 errors 10% of the time. Another way of thinking about this is the confidence levels. If I'm making errors 10% of the time, I'm making correct decisions 90, 95, and 99% of the time. Right? So if I'm told that I want to do this hypothesis test at an alpha of 0.05, or the 5% significance level, I'm also saying that I want to be able to either reject or fail to reject this hypothesis with 95% certainty. So I'll try to keep going back and forth, right, between significance and confidence levels. You'll notice we typically want to check at significance levels for low levels of alpha, right, or the probability of making type 1 errors is relatively low, which if we keep the probability of making type 1 errors relatively low, we're kind of the same way of saying that is we're saying things with a high level of confidence, right? Or a high level of confidence that we're not making these type 1 errors, okay? So, go back to these steps. Once I have the significance level chosen that I want to do this hypothesis test at, and I can do it at several different levels. I'll show you in Excel today, we could do it at several different levels. We'll calculate our test statistic based off the sample mean that we found, right? So we're going to see some sample mean. It's going to be the best guess of where this population mean is, or it's going to be the evidence for which we can start to say whether or not these assumed true values for the population mean are likely or unlikely. Right? So we can take that test statistic, turn it into a p-value. That p-value tells us the probability we saw the sample mean that we did given what we assume to be true if that in fact was the true population mean. Okay? Once we have that p-value, it's representing a probability. So if the probability of seeing the sample mean that we did or anything further away from that assumed true value, if that p-value, that probability is relatively low, lower than the type 1 errors that we want to make, then we're okay rejecting the null hypothesis, right? So that p-value is less than alpha. That was our decision kind of rule for whether or not we reject the null hypothesis, okay? So let's go to an example here. Let's say I've got some group that puts out that back to school spending is on average this year $606.40, right? So they got this from a sample of 30 different families. They found a sample mean for those families of $622, and it's kind of known. And here, this is where I said we have to set this up. I'm just going to, knowing the population variance isn't going to be likely in this type of a scenario, but we have to work through some examples where we have that before we kind of move on to what happens if we don't have the population variance. Kind of like we do with confidence intervals. Right? So let's assume we know this population variance, but we don't know the population mean. Right? So we want to test whether or not back to school spending is different than this reported amount. So anytime we see differs or different than, we're saying, is the amount any other value other than $606 or whatever the stated value is? So this differs or different than, every time we see that, we should be thinking, okay, if we want to test for whether or not it's different than $606, that's just, is it not equal to that, right? Is it equal to any other value? So if that's what we want to test for, we'll assume the exact opposite is true, kind of stack the deck against ourselves, just like with a court case. We want to find someone's guilty, we stack the deck against ourselves and assume they're innocent. So we'll assume that the true population mean is exactly equal to that reported value. So we'll assume that that population mean is equal to $606, which means the alternative hypothesis has to be the complement of that, which is just that it's not equal to that value, any other value other than $606. Now, when you're looking at and you're kind of trying to identify what your null and alternative hypotheses are, you should be using some reported amount. You should not be using the value that you see from your sample. The value you see from your sample, that sample mean, is the evidence for which you're going to try to be able to reject or fail to reject reported values or assumed true values. Okay? So seeing that $622 in here, you shouldn't have the sample mean as the value that you're testing the hypothesis against or for. So we know that we've got kind of this is going to be our null alternative hypothesis. So what type of tailed test do we have here? Not equal to sign. So is it two-tailed or two-sided test, right? Because if I see a sample mean that's what, 640, that goes against the assumed true value because it's not $606. If I see a sample mean of 589, well, that goes against the assumed true value as well because it's not exactly $606. So evidence on either side, right, would be inconsistent with the null hypothesis here. So we've got a two-tailed test. So automatically what we should be thinking about is that we could see evidence on either side of that assumed true mean, and it would go against the null. So if the true population mean was in fact that assumed true value of $606.40, we're going to see evidence on one side of it, but we're going to have kind of two tails. Now, the value that we saw as our sample mean was what? $622 and some odd change. Right? So what we want to find is what was the probability I saw something that far away from the assumed true mean or even further. Right? Well, I only have one sample, but I know that if I take a sample and I see $622, it was equally as likely that I saw something that was that far away from the population, that far away from the assumed true population mean, but below it, right? So if I find this probability, that's telling me the probability I saw something that far away from the null hypothesis that went against the null. Well, with a two-tailed test, everything here would be something that far away from the assumed true mean that went against the null. But everything down here would also have been evidence that was that far away from that assumed true mean, but also went against the null. Right? So what's the exact value here? 62 to 0.85. So 0.85. I probably forgot to throw my, oh, I didn't. So if we look at the difference between these two, right, it's 1648. So if I go 16.45 above, that's how far away the sample mean I saw was. So if I go that same amount down here, you can think about it was equally as likely I could have seen a sample mean that was just as far away from the assumed true mean, but below it. Now, you don't have to actually calculate that value if you don't want to in practice, because what we're going to want to do is turn the sample mean that we found into a test or a z statistic. Once we have that z value, we're dealing with a value that comes from the standard normal distribution. We can find the area to the right, and since we know this is symmetric, right, these areas would have to be the same, and we can simply multiply that area by 2. Right? So let's try to turn this into a test statistic. Remember, what we had here was our test statistic equation is always take the statistic you're interested in. Usually, we would subtract the mean. Here, we don't know the population mean, but we have an assumed true value for it. And then we divide by the standard deviation of our sample mean, right? Or the standard deviation of whatever statistic that we're looking at. Now here, I would have to do an intermediate kind of calculation, which is I know that the square root of my sample means is the population variance over my sample size. I don't remember the exact numbers from the slides here, but I think it was what? This was sample size, I think was 30, and this was some value that we'll see in just a second, right? But once I have that, I can plug that into my denominator. I have the assumed true mean. I have the sample mean that I found. So I'll just plug everything into my equation here. Oops. So I plug everything in that equation, and here, the way I have it written in the slide, I didn't kind of calculate the standard deviation of my sample means as an intermediate step. I just plugged it all into one equation, which is fine, right? It'll give me the same answer. Notice what that population variance was, 4,225. So we plug that in, we get this z statistic or test statistic of 1.39. Okay, so I need to look up that z value of 1.3. There we go. 1.39. So I'm going to use my standard normal tables. I go down here, 1.39 is all the way over. So 0.9177. But remember, the table always tells me the area to the left, right? So this z value is 1.39. The area to the left of that was 0.9177? Right? I wanted the area to the right, so I'll simply subtract that 0.9177 from 1. So for a two-tailed test, right, if we find this positive test statistic, we can look that z statistic or test statistic up in the table, but the table always gives us the area to the left. If we want the area to the right, we then have to subtract that from 1. But what else do I still have to do? This is the area of my one tail here. But remember, I had this two-tailed test. So once I find this, I simply multiply it by 2. Okay? Any questions over that? Any step there? We're okay with this? So what this represents, this will end up being my p-value. So the p-value interpretation is, it's the probability that if what I assume to be the true mean was in fact the true population mean, it's the probability that I saw sample evidence as far away from that assumed true mean as I did, or anything even further away, right? And so for a two-tailed test, sample evidence that was this far away from the assumed true mean, or even further, okay? So let's see what that value is. So we look it up, find that area in the right tail is 1 minus, multiply it by 2. I forgot my multiplication sign here. I mean, I guess it's implied, but, and I get a p-value of about 0.16, okay? So if my p-value is 0.16, at an alpha of 0.05, or at the 5% significance level, can I reject this null hypothesis? Well, my p-value is 0.16, right? I can actually compare it to several different alpha values, right? If I just wanted to do it to 0.05, is 0.16 less than 0.05? No, so I failed to reject, right? So the way that this was set up, oops, we go back here. Oh, I didn't give you an alpha, sorry. I was thinking it was 0.05. Well, I'll show you how we can do it for several alphas here in a second. So we identified the null alternative. We ended up calculating that p-value. Even showed you the intermediate steps. We could even, if I asked you for the test statistic, you could have calculated the test statistic, right? So once I have this 0.16, I'm going to test it against 3 different levels of alpha. So this is kind of a weird one. We usually don't use this, but the 20% significance level, the 90%, sorry, the 20% significance level, the 10% significance level, and the 1% significance level, which would be 80, 90, and 99% confidence level. So with 80% confidence, can I reject this null hypothesis? Or can I reject that the true mean is $606? Well, here my p-value is less than 0.2, so yes, I can reject the null. With 80% confidence, I could say that the true population mean for back to school spending is not that $606. It's something else. Now, at the 10% level, 10% significance or 90% confidence, my p-value is not less than alpha, right? So I would fail to reject. Yeah.
Where's the 0, 1?
So I'll come back to this one. This was example one that we did last class. So I'll revert back to that and show you how we can do the same thing. For now, we just did example 2. Sorry. Or actually, I guess I'd call it 3, example 3. All right, so I should have updated this here. Sorry about that. I think I relabeled it because the first one I originally just called it example, and then I decided to go 1, 2, 3 with it. So this is, we're matching it up to the slides, and I'll repost these slides so that this has it. Right? We're trying to line this up with the slide headings. Example 2 was this one we did last class with retirement age, and we had that p-value of 0.0132. The example we started out today was example 3, and this is where we found that p-value of 0.16. Okay. So for the example that we did today, example 3, the p-value of 0.16 is not less than 0.1, so we would fail to reject it, or with 90% confidence, we could not reject the null. At the 90% confidence level, we would actually fail to reject that the true population mean was $606. And of course, if we can't say something with 90% confidence, we for sure can't say it with 99% confidence, right? And we could go through the whole process, the p-value here, well, if it wasn't less than 0.1, it's clearly not going to be less than 0.01, right? So we fail to reject the null at the 10 and 1% significance levels, but we would reject the null at that 20% significance level, right? Now, for the example we did last class, we ended up with a p-value of 0.01. So just another way of looking at this, clearly, if the p-value is 0.01, we can reject when alpha is 0.2. We can reject it when alpha is 0.1, but we would fail to reject with an alpha of 0.01. So even if the probability of seeing the sample mean that we did is 0.013, it seems relatively low, at the 1% significance level, we actually still wouldn't be rejecting the null. Right? So it's pretty difficult, right? Something has to be pretty unlikely for us to see as our sample mean for us to be able to reject the null hypothesis at the 1% significance level. And that's because we'd really be rejecting it with 99% confidence. Right? So those are kind of the 2 examples, how you could test them against several different alpha values. Okay? Now, usually in a problem, you're given like one, like you're asked, can you reject it at the 95% level, right? Or can you reject 95% confidence level? Or can you reject it at the 5% significance level? Right? You're just asked about one specific one. We can think about, we can compare, once we have that p-value, we can compare to any alpha that we want. In fact, what the p-value is really telling us is, I can reject the null hypothesis as long as the type 1 errors I want to make are just slightly above whatever my p-value is, right? Because I could reject all the way down to where that type 1 error, that alpha, is just slightly above whatever p-value I found, okay? Any questions on this before we keep moving? I want to reiterate kind of this relationship between the p-value. Just go over it again. I know that last class was probably a lot. This is kind of a difficult concept. We're going to see a lot of examples. I'm going to say things in several different ways. And so I think over the course of the next few classes, it'll all start to hopefully kind of come together. So let's say we've got these sample means, and I'll even use the example that we just did, right? So 606.4. Let's assume for a second that the assumed true mean that we had, let's say we somehow were able to observe the population mean after the fact, and we see it's exactly $606.40. Like, let's just assume that what we assumed was true. Well, before we were able to actually confirm that this was a true value, if we would have seen sample means that were out here, as far as a sample mean that would have given us, let's say we had a sample mean and it gave us kind of 0.025 in that area to the right of it. It's a two-tailed test, so we've got the same area to the left. What this would really be saying is, if we see a sample mean right here or anything else that was further away, Well, we still could see those values for the sample mean. It was very unlikely, but we still could have seen them. But if we set alpha to 0.05, if we saw any sample mean that was greater than this cutoff here, we would have been, for all of these, getting p-values, right? The area and the tails were getting smaller. We would have had p-values that would be less than 0.05. So for every single one of these values, we would have been rejecting what we assumed to be true, even though at the 5% significance level, even though in fact it was the true value. So kind of when we're setting this alpha, what we're really saying is, look, even if the value we're assuming that is true, if it ends up being the true value, alpha is the kind of the proportion of times that we will be wrong, or the probability that we will make a rejection decision when we shouldn't have been rejecting, right? We'll decide to reject when we should have been failing to reject. So that's kind of why the relationship between alpha and the p-value, what we're saying is if I see a p-value that's, even less than 0.05, so maybe 0.02, I know that I could be wrong. I know that I could be making a type 1 error. But the probability that I saw something that far away from this assumed true value, if in fact it was true, is less than that kind of standard that I wanted, which was if it's less than 5% likely for me to see, or if the probability of me seeing it is less than 0.05, I'm okay rejecting that as the assumed true value. Right? I know I'll be wrong sometimes, but I'm not going to be wrong very often, right? I know that if I set the alpha to 0.05, I'm only making errors kind of 5% of the time. Right? Any questions on that before we keep going forward? All right, we'll keep getting looks like this because got a few more examples. So I'm going to take a step back. We'll do this first and then we'll go into Excel. We'll kind of end the class with Excel. So we can do the exact same thing that we were doing for the population mean for the population proportion, right? The only thing that changes is when we write out that null and alternative hypothesis, right, the notation is going to be a little bit different. But we would still have our right, our left, and our two-tailed test, or our greater than, less than, not equal to tests. Remember, the test, is identified kind of off that alternative hypothesis. Greater than sign, we have a greater than our right-tailed test. Less than sign, less than our left-tailed test. Not equal to sign, not equal to, or a kind of a two-tailed, two-sided test. Okay? Same kind of rules apply. The steps are going to be similar, but instead, I'm going to show you how if we didn't do the p-value approach and we instead used what we call the critical value approach, I could also make my rejection decisions. So just because now I'm combining proportion examples with the critical value approach, you can use either approach regardless of whether or not it's a proportion or a population mean. Okay? So with the critical value approach, it's going to be a little bit different. The first two steps are the same, right? Identify your known alternative, figure out what your alpha level is. Using alpha and the type of test that you have, so left, right, or two-tailed, you then find a critical value and a rejection region. Okay? So what that's going to look like is you're going to try to find using that standard normal distribution, you're going to try to find a critical value and then a rejection region such that if your test statistic is in that rejection region, you'll reject. If it's not, you'll fail to reject, right? So once I have the sample mean and all the other information, I can figure out if my test statistic is in that rejection region or not. And all I'm doing there is plotting things. I'm plotting my critical value, I'm plotting my test statistic. If that test statistic is in my rejection region, I reject. If it's not, I fail to reject, okay? So that's the idea of what we're doing there, right? So once I find that critical value, I figure out what my test statistic is, I kind of figure out if that test statistic is in that region. Now, the one thing that's going to be a little bit different is the equation that we have for our test statistic, because we're no longer dealing with sample means, we're dealing with, we're no longer dealing with population means, we're dealing with population proportions and where we think that's going to be at. So here, notice my Z statistic, it's still a Z value. It's still coming from that standard normal distribution. It just looks a little bit different than what we had before. So why does it look that way? Well, let's make a comparison to what we were doing before. We said before, when we wanted to calculate this test statistic for a sample mean, we took the statistic we're interested in, subtract the assumed true value for the population statistic, and then here we divided by the standard deviation of whatever statistic we were interested in, here the sample mean. It just so happened that the equation for the standard deviation here was like this. So you can kind of call them maybe here. If I'm going to calculate a test statistic for my proportion, well, what do I observe? I observe from my sample a sample proportion. I will then subtract the assumed true population proportion, right? Really the same thing, it's just looking at a different statistic. And then I'm going to divide by the standard deviation of my sample proportions. Well, if we go back to confidence intervals, we already had something for this. Now, the one difference is, before, when we looked at a confidence interval, the best guess of what that population proportion that we had was our sample proportion. But now we don't have to have kind of a best guess because we're assuming that population proportion is a certain value. So now instead of using kind of that sample proportion, we're using whatever the assumed true value is for that population proportion. Okay? But really, it's like the same format, right? Subtract the assumed true value, divided by the standard deviation of the statistic that you're looking at. All right, so how do we find these critical values? I kind of gave you the idea of what we're going to do with them, but how do I find what that actual critical value is? All right. So we've talked about, I build this rejection region. If my test statistic is in the rejection region, I can reject. Right? Well, how we find these critical values are going to be whatever value, whatever Z value gives us our alpha or our type 1 errors in the tail. Right? And if it's a two-tailed test, it's what critical value gives us alpha kind of in the tails. Right? So it'll be a little bit different when we have a two-tailed test. So if I have a right-tailed test, I should be thinking about my test statistic. I want to get alpha in the right tail. So if I want to get alpha in the, actually I'll come back to this because I think the visual here is going to be a lot more beneficial. So if I have a right tail test, what that's telling me is that only evidence on the right side of the distribution would go against the null, right? Because with a right-tailed test, my alternative hypothesis is that it's greater than a certain value, but the null is that it's less than or equal to. So the only evidence that would go against that null of being less than or equal to is if, in fact, I find evidence that's above the mean. Well, if I find something that's above the mean, remember, these test statistics, these Z statistics, they're still Z values. They no longer represent the number of standard deviations away from the true population mean, but they represent the number of standard deviations away from the assumed true population mean, or in this case, the number of standard deviations away from the true population proportion, or sorry, the assumed true population proportion. So if we find something above that assumed true value, it's going to have a positive Z statistic because it's a Z value and it's above the mean. And the mean for the proportion would be, the true population proportion. So if we find, if we want to find the critical value that gives us the alpha that we've specified in the upper right tail, well, how could I find that? If I know, let's say alpha is 0.05. If I know the critical value is a Z value that essentially represents a cutoff for if I see any test statistic above that critical value, I can reject. If I see anything below it, I fail to reject. How could I find that value? If it's coming from the standard normal distribution, and I know the area I want in the right tail is 0.05, how could I use the table to find that? Yeah.
You could just find where the Z value equals whatever the percentage is above.
Yeah.
Or 1 minus it.
You're right. So it's going to be a little bit tricky with the right tail test, right? Because if I looked up 0.05 in that table, so go to my standard normal or my Z table, I know the area I want in my tail is 0.05. Well, the problem is if I look up 0.05, it's in between these two. So negative 1.6. Well, didn't I just say it has to be a positive z-value? Well, yeah, because when I look up the table is always looking at the area to the left. So if I want 0.05 in this upper right tail, to find the value that would give me that, I actually need to look up 1 minus that alpha, right? Because the area to the left of that critical value is the area that I have to look up the area to the left in that table. So here I'd look up 0.95. So I go here, I look up 0.95, looks like it's in between these two, so 1.64 and 1.65. Same kind of convention, if we're in between two, we'll just take the higher of the two, so 1.65. So 1.65 is going to be my critical value. So I'll say that if I calculate my test statistic, and my test statistic is anywhere above 1.65, I'll reject. If it's anything below 1.65, I'll fail to reject. Okay? Any questions? Yeah.
So is that just taking the p-value method and just subtracting the last step and just?
So it's, where are we at in time?
So instead of like finding the p-value, you just find the test statistic, and if anything is above that, you reject it.
Yeah, I'll compare the two here in just a second, but it's a good question. I understand what you're asking, but we'll hold off just a second, okay? Because it's a little different than that, but it's you're close. So we've set this rejection region. If we now calculate the test statistic, if it's anywhere here, we reject. If it's not, we fail to reject, right? Now, if we were dealing with a left-tailed test, finding the critical value is pretty easy, because now I want alpha in my lower left tail. And I want to find the value, the critical value that would give me that desired alpha in the tail. Let's say we keep using the same alpha. I actually don't even have to go to the table to look this one up. What would the critical value be for a left-tailed test at the 5% significance level? The area to the right of a z-score of 1.65 is 0.05. What z-score would give me an area to the left of 0.05? Yeah, this is a symmetric distribution, right? I'm dealing with that standard normal distribution. So I know that it'd actually be the exact same value if I'm looking at the same significance level. But for a right-tailed test, it would be positive. For a left-tailed test, it would be negative. Right? So for my left-tailed tests, I'm always going to have negative critical values. For my right-tailed tests, I'm always going to have positive critical values. Okay? What about for a two-tailed test? It's going to be a little bit different, right? So for a two-tailed test, right, and I'll leave this down here just in case someone's still looking at it. Now, when I think about alpha, let's say I still want my significance level to be that 5% significance level. With a two-tailed test, I actually am going to have not one critical value, but I'm going to have two critical values, right? Because evidence on either side went against the null. So now my alpha is the area in both of these tails. So how much is in each tail? Alpha over 2. And it starts to look really similar to what we were doing with confidence intervals, right? Because now when I take alpha divided by 2, now the area that I look up in the table is alpha over 2. So let's say I did alpha as 0.05. What's the critical value? So I go to my standard normal table. Alpha of 0.05. Well, I have two tails, so I divide it by 2. So I want 0.025 in the lower left tail and the upper right tail. So I look up 0.025. It's right here. So negative 1.96. So for a two-tailed test, I can just look up alpha divided by 2. That will always give me kind of the negative critical value. And then I just have to remember, oh yeah, I also have a critical value up here, right? That's the exact same thing, but positive. So for a two-tailed test, we'll have a pair of critical values. They'll be the same value, but one's positive, one's negative. Okay. Any questions on that before we kind of keep moving a little bit? And then I'll come back to your question. I haven't forgotten. So this is kind of what I just said, written out mathematically a little bit more, when do I reject? Well, I think it's easiest to just draw the picture out if your test statistic is in that rejection region. But another way to think about it, in any scenario, what I could kind of summarize this as, if you take the absolute value of your critical value and the absolute value of your test statistic, it's always going to be, is your test statistic greater than your critical value? If it is, you can reject. It's just when we're doing the left-tailed test, the reason why we have to take the absolute value is because the test statistic being like more extreme than the critical value is actually being a larger negative value, which would actually mean it has to be less than, right? So instead of like kind of flipping back and forth, depending on the type of test, just always think about it as, if I were to take the absolute value of both my critical value and my Z statistic or my test statistic, if the test statistic is greater than my critical value after I've taken the absolute value here, then I would reject, right? Because it doesn't matter. If my test statistic is over here, let's say it's 2.5, well, once I take the absolute value, I can see that, oh yeah, the test statistic is larger than my critical value. It's in the rejection region. But if I had seen instead a test statistic of negative 2.5, well, there I'm not looking for, is it greater than? If I'm dealing with the negative values, I'm actually looking to see, is it less than? But if I take the absolute value of these two, right, then it goes back to like this works, right? Once I take the absolute value of your test statistic is larger than the absolute value of the critical value, you'll reject, regardless of the type of test, left, right, or two-tailed test. Okay? This is just kind of a summary of what we talked about as well. That we're always going to end up with positive z-scores for the right-tailed test, negative z-scores for the left-tailed test. And then we have to divide alpha by 2 when we're looking up the critical value for a two-tailed test, which would give us a pair of critical values. Remember, these critical values are z-values. They're like cutoffs. Like if I see a test statistic greater than this, right? So critical values and test statistics are both z-values. They're both coming from the standard normal distribution. It's just your critical value is like, you're saying, here's the cutoff for which if I see a test statistic or a z-statistic any greater than this, or any greater than this in absolute value, then I'll be rejecting. Right? But they're coming from the same, they're both representing kind of z values there. What do we want to say here? I think this is just kind of, we can do the exact same thing if we had sample means. So I want to think about this. We've kind of already talked about this, how we find these rejection regions, right? How they look different. For a left-tailed test, we have a negative z-value, right-tailed test positive, two-tailed test, we have a pair. This is all kind of summarizing everything that I kind of had up on the board, just looking at it a different way. Okay? So the steps, once again, it's exactly what we were doing for the first two. We can even like flip-flop 3 and 4. So you can calculate your test statistic first, and then instead of taking that test statistic and finding a p-value, you just find your critical value. And then instead of comparing a p-value to alpha, you now compare your critical value to your test statistic. Right? So we'll go to this example in just a second, but I want to try to answer Holden's question here. I'll probably draw this several times. Not today, but throughout the next couple of courses or classes. So what were we doing with the p-value approach? Let me make sure that's a little bit too high. So actually, I'll do this for sample proportions. So we were seeing some value, and I'll do this for a right-tailed test just to simplify here. What we were doing was, with the p-value approach, we were finding this area, right? The problem was, if I just had the sample proportion, I don't have a table for that. I only have a table for a standard normal distribution. So what I would have to do is convert that sample proportion into a z-value, or into a z-statistic, right? My test statistic. Once I had this test statistic, I could find my p-value. So I could think about this as, my test statistic is really, the test statistic is associated with whatever p-value I'm going to find once I look this up in the table. Right? Anytime I look up that test statistic, I would find the exact same p-value for a right-tailed test here. Right? I could then compare that p-value to alpha. If it was less than alpha, I would reject. What am I doing with a critical value? What I'm doing with my critical value is I'm saying, okay, look, there is some critical value. Well, I need to leave myself a little bit more room, so I'm going to draw this out a little bit more. Because I think this really helps think about this. So let's say my critical value, it's not really drawn very well to scale, but let's say my critical value is all the way out here. The critical value that I'm going to find is associated with whatever alpha I've kind of specified, right? How did I find the critical value? Well, I had to know the area I wanted in my tail. What area did I want in my tail? Whatever amount of type 1 errors I was willing to make. That was alpha. So once I find that critical value, I know that it's the value associated with seeing alpha in that upper right tail. Right? So notice, when I use the p-value approach, I was comparing the area in the tail, the p-value, to kind of my cutoff area in the tail, alpha. Right? I was comparing the areas in the tail when I use that p-value approach. When I use the critical value approach, I'm comparing my test statistic associated with that p-value to the critical value that's associated with the specified alpha. So it's almost like, you know, the critical value approach, I'm comparing the z-values here. P-value approach, I'm comparing the area in the tail, or the probabilities kind of seeing these values or anything greater. Okay? So it's kind of like two ways of looking at the same thing. You could almost imagine, and the reason why this works is because when I go to that standard normal table, if I look up a z-value, I'm always going to find the same area in the tail, right? So I know that these two are like linked. I could almost think about this as if I took all my z-values and like plotted those on my x-axis, and then I took all of the area to the right of those and plotted them on my y-axis, right? Well, I'm really just like comparing, I mean, it doesn't, I can always trace this exactly to one specified value. So I don't know, it's you know, we're really, it's almost like if I had two values and I had a function and I put the values in the functions, we always know for certain functions that it's going to be greater than, you know, if x1 is greater than x2, then when I put these into the function of x1 will always be greater than the function of x2, right? We get real mathematical into this if we wanted to. But really, I think the visual here is nice, right? Critical value approach, I'm comparing z-values. I have a cutoff z-value associated with seeing the type 1 errors alpha in the tail that I want. I have a test statistic, right? I can compare those two z-values. Or I can compare that area I want in the tail alpha to the area in the tail for whatever sample evidence I found, which that would be my p-value. Right? So it doesn't matter if I compare the p-value to alpha or my test statistic to the critical value. Both ways will kind of lead me to the same decision. Okay? Does that answer your question? Is that kind of any other questions on that? Okay. So let's try to work through one sample proportion example. Oops, I didn't want to do that. We'll then work through a few more next class, and then we'll do a lot of Excel, hypothesis testing Excel on Friday. Okay. So I have kind of a weird one here, but I want to use it to prove a point. So let's say you want to test for the hypothesis that whether or not there are more than 50% of the population that owns a gun, right? So that's what you want to test for, right? So you'll assume the opposite is true. So if I want to see whether or not the true population proportion is greater than 50%, I'll assume the opposite is true, which is that it's less than or equal to 50%. So what do I assume to be true? That's my null hypothesis, right? So I've assumed that it's less than or equal to 50%. Remember, what you want to test for, or what you're trying to find, if I'm trying to find someone's guilty, I assume the opposite is true, which is that they're innocent. I want to test and I want to find if that true population portion is greater than 50% or greater than 0.5. So I assume the opposite is true, which is that it's less than or equal to that value. So what type of tailed test do I have here? Yep, greater than sign in the alternative hypothesis, so right tail test. Right. What would my critical values be? Well, for a right tail test, I could look up 3 different critical values. I would have the alpha of 0.01, alpha of 0.05, and alpha of 0.1. Now, if you go back to this earlier slide, I actually put them all up there. When we look up those same 3 values, well, maybe somewhere, I'm always going to, if I look up these same alphas, I'm always going to find the same 3 values, right? So for a right tail test, they end up being 1.29, 1.65, and 2.33. Okay? You don't have to memorize those. I could actually go to the table, look up that area I wanted in the tail of 0.05, right? Find the corresponding kind of Z value. Now, if I look up just alpha here, remember, that's the area in the left. For a right tail test, it would be that same value, but positive, right? Because the area to the left I really would want was 0.95. So we could look up those critical values. Now, if I had like options here, the only ones I should even be thinking about as possible answers for a right tail test would be positive Z values. So only A and C really make sense here. C ends up being if I divided alpha by 2, but I know that I should only divide alpha by 2 if I'm dealing with a 2-tailed test. So I'll find those critical values of 2.33, 1.65, and 1.29. What's our test statistic? Well, this really just becomes like, especially once we get to the exam, you have the formula sheet. It's really just going to become, I've got this formula. I've identified my sample proportion, which I think if we go back here was what? 0.41. Sample size is 100. That assumed true proportion was 0.5. It's really just a matter of plugging those in, right? So sample proportion of 0.41, assumed true proportion of 0.5, and my sample size of 100, right? So if we do that, we get negative 1.8. Now, I found my critical values. I found my test statistic. What I want to do at this point, go back here so we remember. Here's our critical values, and here's our test statistic. Okay. So what I'm going to do is I'm just going to draw a standard normal distribution, and I'm going to plot those. Okay. So here's my standard normal distribution. My critical values were 1.29, 1.65, and 2.33. Right? And I'll kind of use these arrows to kind of indicate my rejection region. I found a test statistic of negative 1.8. So what levels can I reject at here? I guess it's kind of a trick question, but if these are my rejection regions, there's my test statistic. What levels can I reject at? None of them, right? Well, right away, I should have known this. I don't even know why I did any of this work, because if I go back to the original problem, if I'm assuming that that true population proportion is less than or equal to 0.5, I then found sample evidence that supports the null, well, then for sure I shouldn't be rejecting the null, right? Which is what we end up figuring out, but I mean, we didn't even have to go through this whole process if all I wanted was the rejection decision, right? If all I wanted was the rejection decision here, I found sample evidence that supports the null, so I didn't even have to go through any of this work. But if I wanted to prove to myself that even if I follow the steps, I will end up kind of rejecting it, sure enough, with our critical values and our test statistic, you know, we have a pretty nice visual that we're going to be rejecting the null here. Okay? Or sorry, not rejecting it. That we'll be failing to reject the null here, right? I could have also looked up that test statistic of negative 1.8, right? On my standard normal table, so negative 1.80. The area to the left of that is 0.0359, and this is kind of a weird one. But if I wanted the p-value, remember, it's a right-tailed test, I actually wanted the area to the right, which would have been my p-value, or 1 minus that 0.0359, so 0.9641. So I get a p-value here that's huge. Well, remember, we only reject if the p-value is less than alpha. A p-value of 0.9 is not going to be less than any alpha we have, which makes sense because we found evidence that supported the null hypothesis here. Okay. I'll leave it at that for today. We'll do, I think, 1 or 2 more proportion examples by hand, and then we'll do a lot of work in Excel on Friday, okay? And after Friday, I'll probably post the next Excel assignment that we can start working through with hypothesis testing.